In part 1, we saw the basic technique of resistance welding, how electrodes are placed on either side of the job and a large current is passed, the resistance of the metal generating enough heat to fuse a small area into a spot weld. This is called direct spot welding, and it's used very successfully throughout industry on jobs large and small and with thick and thin gauges of steel, stainless steel, heat-resistant steel, brass, aluminium alloys and titanium. But it's obvious that there are some jobs where it just isn't possible to have a welding electrode on each side, and others where it would be very convenient not to have to do it that way. In fact, there are quite a number of applications of resistance welding where the basic method has been modified in various ingenious ways to make it very versatile indeed. Here's the normal direct weld as you know it by now. Current passes from the transformer to one electrode through the workpiece directly to the opposing electrode on its way back to the transformer. But the welding current can be arranged to flow in different ways to provide what are called indirect welds. If we replace the lower electrode by a copper backup die, we can still pass a high enough current to fuse the metal into a weld. This current is collected from the job by a contact block on the same side as the electrode. And it means we can weld jobs like this. Of course, the contact block must be far enough away from the electrode not to cause any serious shunting of the current. An obvious development is to replace the contact block with another electrode and so make two welds at once. Because the current flows through each weld in series, the technique is called series welding. Incidentally, if the lower sheet of metal is thick enough to carry the necessary welding current, we can sometimes dispense with the backup die entirely. And series welding can be taken further. Here are 4 welds at once from the same current path. For jobs like car body repairs, a portable series welder is particularly useful compared with standard static equipment. But there's quite a range of portable spot welding equipment for all sorts of special jobs. Now what about a case like this, where we need a regular row of uniform spot welds? Why not make the electrodes into wheels? The metal is rolled between the wheels, under pressure of course, and stopped at regular intervals. At each stop there's a pulse of current and a spot weld is made. This is intermittent motion roll spot welding. It gives uniform welds at regular intervals and with the same pressure throughout. On a titanium jet engine part, very close tolerances are achieved with the aid of external water cooling. We can take roll spot welding a stage further too, by rolling continuously and arranging the pulses so that the welds overlap. We can produce a continuous seam weld. This is the fastest and cheapest way of making pressure-tight seams in thin-gauge material. Petrol tanks and domestic radiators are typical products. It works well too on awkward shapes with tight corners. A very similar process is stitch welding. The work is advanced by hand while the electrode tips are opened and closed automatically. The spot welds overlap to make a seam. Here's the system known as projection welding. The electrodes, in this case, are flat copper alloy surfaces or dies. They supply the current and the force, but they don't determine the position of the welds. The weld points are predetermined by dimples formed in one of the sheets to be welded. When the current flows, the only points of contact are the dimples. These melt and collapse to form the welds. To increase the life of copper alloy electrodes, sintered copper tungsten inserts are usually fitted in the dies opposite each weld position. Since a large number of welds is made at once, the machine must be able to supply a very large current and a hefty electrode force. Projection welding is ideal for attaching threaded nuts to thin sheet, and for jobs which supply their own contact points, like these inspection lamp cages. Even the extra cost of preforming these projections on such items as rocker arms and some types of tubular furniture is outweighed by the saving in welding costs. Specially formed electrodes can actually hold tiny parts like these in their exact location while the weld is made. Resistance welding has now largely replaced the traditional soldering and bracing in the assembly of radio valves and transistors. We have two more techniques which rely on resistance at the junction of two pieces of metal held in electrode clamps under moderate pressure. In resistance butt welding, the parts are brought together before the current is applied. They soften and weld, then cool before pressure is relaxed. Flash butt welding differs only in that the current is already on as the ends come together. This causes a series of arcs which generate intense heat. As the metal melts, the pressure is increased, squeezing out the molten metal and slag to form a high-quality joint. Then the excess metal is skimmed off. When joining a high-speed steel broach to its mild steel shank, annealing the junction follows automatically. Flash butt welding is used in jobs like small pipe elbows and aluminium spool flanges, and road wheel rim joints where a long seam is welded in a single spectacular flash. You will find resistance welding in all its many forms around every corner in industry. Straight spot welds on wheels and storage bins, and alongside projection welds for captive nuts. Spot welds on top, stitch welds round the base of a domestic iron. Seam welds seal off complex shapes. The barrel of this shock absorber is seam welded and the ring fixed by projection welding. Projection welds are made either individually on electrical contact tabs, to coarse industrial rigs, or multi-projections on ball bearing cages, industrial steel flooring, and bird cages. But no matter what form it takes, the principle of resistance welding is always the same.